Hi. So we'll begin with something called contractible space in this lecture. So as from the name, you can figure out what should be the condition for this contractible space. That means, suppose we have a topological space X and there should be a certain point, let's say C naught, in the topological space X, such that from each direction, if you apply some force, it should gather at this particular point, small x naught. Okay, it will be contracted. That means all the other points on the in the topological space X except C naught will overlap with C naught. So what's the mathematical terminology of this contractible space? So that basically means that I define a continuous function identity map that is from X to X, and this particular identity map should be null homotopic. So null homotopic means there exists f naught is a mapping from X to X such that f naught of small x equal to C naught, and identity of X is homotopic to f naught. Or more clearly to say, there exists capital F from X cross I to X such that f of x comma 0, it is identity over X, and f of x comma 1, this is C naught. In fact, it is same as f naught of x. Okay, so that is actually means by the null homotopic. So you see that suppose we have a contractible space like this, and let's take any point, particular point small c naught, it is my f, and let us take another continuous map, let's say it is G. Right? Now you see that if you take any two point here, see this f and C naught, if you take any two point here, you can, if you join this by C naught, any point on this f can be joined by C naught, and this can be joined by G on G also at certain point on G. That means by this kind of structure you should always get, and that can work as a homotopy between f and G. So the corollary that should be mentioned for this purpose is the following, that suppose X is a contractible space, X is a topological space, then X is contractible if and only if any continuous function functions, let's say f comma g from X to X, is homotopic. Right? So the justification is always easier. Like one side is very clear. In fact, suppose we take any identity map X and a constant map C naught, then both will be homotopic. So that will imply that X is contractible. But what about the converse one? In fact, this is the converse statement. But what about the straightforward? So straightforward statement is something like, suppose f comma g are mapping from x to x, be continuous maps, right? Then I already know that identity of x from x to x and f naught from x to x, such that f naught is basically mapping everything at c naught. Okay, these two are homeotopic, are homotopic. Now identity of x composed with f, this is homotopic to f naught composed with f. We have already seen that the homotopy property is preserved by the composition from either from left side or from right side. Similarly, identity of x composed with g is homotopic to f naught composed g. Now note that f naught is a constant map, so f naught and f naught are just same. That means I can call this as small h, I can call this as small h. So both are homotopic to small h. I mean this one and this one, both are homotopic to small h. So identity of x composed with f, these two are homotopic to identity of x composed with g by symmetric transitivity property. Now identity of x of f is nothing but small f is homotopic to small g. So note that I have mentioned here f and should be small x, capital X from capital X. What if I change the topological space y? Means if I take any continuous functions from y to x, then also will be this property satisfied? The answer is yes. For any topological space, if I can replace this as y, for any topological space y, if f and g are continuous maps from y to x, then x will be contractible if and only if f and g are homotopic to each other. Okay. In fact, in that case, the maps will be the domain maps will be changed. Like my f naught composed f will be mapping from domain of f is nothing but y to codomain of is x, right? And similarly f naught composed g is mapping from y to x. Okay. So that means the contractible space means whenever I take any two continuous functions like this, both will be homotopic to each other. Okay. Now let us move to some applications on homotopy theory, and the most crucial application of homotopy theory that plays a central role in studying geometrical objects is nothing but the fundamental group. So what is a fundamental group? Fundamental group means if you have a topological space X, this basically is a connection from the category of topological space X to category of groups. Okay, means if you have any topological space X, you can get its fundamental group in the group category of groups. Let's say it is G for now, denote it as G. Okay, and most importantly, this X should be path connected. Okay, so that means whenever you path connect topological space X, then if you want to study its property and some basic property which is not feasible in studying in topological setup, you can move to the group setup, like taking its fundamental group. So first let us know what is the construction. So I just recall some basic things, like what is, suppose gamma is a mapping from the closed interval 0 comma 1 to x, where x is a topological space, then is a continuous function, then gamma is said to be a path joining gamma 0 and gamma 1. Means suppose in x, in topological space x, let's say you have any 2 points here, let's say a and b, then any continuous function from in the topological space such that gamma from 0 comma 1 to x, such that the initial point is a and final point is b, then it will be like this. So it is the path from a to b. Now we already have the notion of homotopy between the continuous functions, so we can extend the same statement in case of studying homotopy between two paths in a topological space. That means suppose we have a topological space x and gamma 1 and gamma 2 both are continuous functions from 0 comma 1 to x, but such that the condition is that gamma 1 0 is same as gamma 2 0 and gamma 1 1 equal to gamma 2 1. Note that this gamma 1 0 and gamma 2 0 both are called final point. Like if you have any path from a to b like this, then a is said to be initial point, b is said to be final point. So whenever you have a two continuous functions from 0 comma 1 to x, means a path in topological space x whose initial points and final points are same, in that case gamma 1 and gamma 2 are said to be homotopic if and only if there exists f is a mapping from not x, it is I cross I to x, such that f of s comma t, f of s comma 0 is gamma s gamma 1s, and f of s comma 1, this is gamma 2 s for all s belongs to I. Okay, so that means that so the picture represents the following, that suppose you have a topological space x and let us take, this is my one point, let's say it is a, this is b. One path is like this, another path is like this. Okay, so then each gamma s will be the following from, like what we get from here, that if t, for example, suppose we defined gamma t is mapping from I to x, such that gamma t of s equals f of s comma t. So what is gamma 0? So gamma 0 of is nothing but f of s gamma 0, nothing but gamma 1 s. And similarly gamma 1 is mapping from I to x, such that gamma 1 of s equal to f of s comma 1 to gamma 2s. So that means all the maps will be the following, that these are the in between gamma t's. Okay. Whereas the initial one is gamma 0 and this one is gamma 1. Okay, so like this is the way. Yeah, so I mean, okay, let us name this as gamma bar, gamma t bar. So this is my gamma 0 bar, gamma 1 bar. So I'm just reparameterizing the gammas, right? Okay. Now this is the condition that once we can, how I can define the homotopy between two continuous functions. I mean, in fact, two paths in topological space X. So as usual, that if I consider, suppose x0 comma x1 belongs to X, and suppose path from X comma x0 to x1, this is set of all paths from I to X such that f of 0 is x0 and f of 1 is x1. Okay, so if it is set of all paths from paths in the topological space X, in that case I can define equivalence relation that is nothing but homotopy. Homotopy property. That means I define f1 is homotopic to f2, I mean is equivalent related to f2 if and only if f1 and f2 are homotopic. These two are paths in X. Okay, so you can check that both are is equivalence relation. Just a short check. So let's take f is from I to X is a path in X. Then we define capital F is from I cross I to X such that f of s comma t is itself small f of s. In that case, f of s comma 0, this is f of s as well as same as f of s comma 1. So this reflects that the relation is reflexive, and in fact symmetricity is also clear. For example, suppose we have f is homotopic to G. Let us consider capital F is from, so capital F is mapping from I cross I to X such that f of s comma t, f of s comma 0, small f of s, and f of s comma 1, this is small g of s. Now we define another homotopy map. Let's say f1 is from I cross I to X such that f1 of s comma t, so it is same as, it should be g of s, not, I mean, like, I should define f1 from I cross I to x such that f1 of s comma 0, this should be same as g of s, and f1 of s comma 1, this should be same as f of s. So it is enough to define f1 of s comma t as f of s comma 1 minus t, right? Then you see that this condition is satisfied and this one is also satisfied, because f1 of s comma 0 is nothing but f of s comma 1, nothing, which is same as g of s. So this reflects that this is symmetric and let f is homotopic to g and g is homotopic to h. Okay, let us define f1 is from I cross I to x such that f1 of s comma 0 is f of s and g of f1 of s comma 1, this is g of s. Similarly, f2 is I cross I to x such that f2 of s comma 0, this is g of s, and f2 of s comma 1, this is h of s. So I will just join these two paths. Means suppose we have, here is one, here is another one, and here is also another one. It is my f, this is my g, and here's my h. Okay, so what are the intermediate steps? For example, consider, let us, these are the intermediate steps from f to g. And let us consider these are the intermediate steps from g to h. So once I will traverse from f to g by f1 and then from g to h by f2. So once I will concatenate all these intermediate steps, that means by first half time I will traverse from f to g, and by next half time I will traverse by g to h via f2. So the joining map is the following, that f is from I cross I to x such that f of s comma t is nothing but f1 of s comma 2t and f2 of s comma 2t minus 1. Note that the first small s, this actually represents the orientations, and the t is actually represents the time at which it is traversing. So here it is when t belongs to 0 to half, and here's t belongs to half to 1. So what about f1, I mean f of s comma half, because only these are the intersection region, so it's nothing but f1 of s comma 1 and same as f2 of s comma 0, same as g of s. Okay, right. So this actually reflects that it is transitive. Okay, so symmetric, transitive, as well as reflexive. So all three conditions actually implies that it is equivalence relation. All right. Now what is, suppose now by a path I can, suppose we have a topological space X, and okay, so now let us name this as special kinds of path. So one kind of path you can think of it as a loop, right? So what's a loop? Loop is like this, means just fix a point, traverse like this, and I can come back to here. So that means, suppose you have a particular path like this, and then join the final and initial region at certain point. That is a loop. So that means a loop is nothing but gamma from 0, 1 to x, such that gamma of 0 is same as gamma of 1. Is a loop. So as it is a loop, so what are the conditions in what are the conditions of homotopy property in group? That is same as the topological, same as the path in general path in topological space. But the picture is the following: that suppose you have a particular loop like this. So any other loop which will be homotopic to this particular loop, let's say name this as gamma 1, any other loop will be like this. So it is the same orientations. Okay, this one, but you cannot say that it will overlap at a certain point like this. No, you cannot say. You can say that it should look like this, or it may go bigger in region as well, like this one. Okay, so we can define homotopy in loops as well. Okay, so in fact the loops are included in the path in topological space X. So suppose gamma is mapping from 0, 1 to X. I consider set of all the maps, let's say delta from 0, 1. Okay, so it's a loop at base x0. So what does this mean, that base at x0? This actually implies that gamma of 0 is same as gamma of 1 is x0. Okay, so delta is from 0, 1 to x, such that delta of 0 equal to delta of 1 is x0, and delta is homotopic to gamma. So this is non-empty because gamma is already there. So the collection of all such gammas which is based at x0, we denote it as pi of x, x0. So this is said to be the fundamental group. So what is the group operation? I'm saying it is a group, so one can get eager to know that what is the group operation that is hidden inside the group. So the operation is the following. So before going to the operation, suppose gamma 1 is from 0, 1 to x, and gamma 2 is from 0, 1 to x, such that I'm sorry, the loop should be like this. I'm very sorry. So if it is my small x naught, so gamma should be like this. So it is my 1 gamma 1, this is another gamma 2, another gamma 3, yeah, gamma 4, and so on. These are the homotopic categories. I am very sorry to give you wrong geometric implications. I forgot that the base point should be fixed. Alright, so let us consider gamma 1 and gamma 2. So I will just concatenate these two paths like gamma 1 and gamma 2. So what is the geometrical approach? So for example, suppose it is my small x naught. I have gamma 1 here, and let's say another map like this, gamma 2. So gamma 1 concatenated with gamma 2 means that in the first half term it will run over gamma 1 and can come back to x naught. Again by next half time it will run over gamma 2 and come back to x naught. So that means this is in the first half time, next half time like this. So this is my path that I should obtain via concatenation. So gamma 1 star gamma 2 is the following, that of t is equal to gamma 1 of 2t and gamma 2 of 2t minus 1, where t belongs to 0 to half, where t belongs to half to 1. Okay, so that is the concatenation. And gamma 1 gamma times gamma 2, that is the group operation, is defined in this way. Is nothing but the fundamental group the homotopic class of gamma 1 star gamma 2. Okay, one can check that this is group. With respect to the operations. So in the next lecture we will define or find out what is the group structure, how to define the group structure and fundamental group. Okay, so I hope this lecture is, you have understood this lecture. Just go through whatever you have studied in the last sessions as well as in this session. We will continue in the next lecture onwards, that how to I will show that how to prove that this is a fundamental group. Okay, all right, thank you very much.